Hello students, hello students, hello students, hello students, and welcome to Edu Math Hub. In this quick revision video, we're talking about magnetism and electromagnetism for JAMB 2025. So let's go. Now, the first thing you want to know about magnets, we'll be starting with the definition of magnets, okay? So a magnet is a material, so that's the topic there, magnets, right? We're talking about magnets now. So what's a magnet? So basically, a magnet is a material, okay, which is always in the shape of like maybe a rectangle, can also be in like a circular shape, okay, that is capable of attracting iron or pieces of steel. So it's capable of attracting iron or pieces of steel. So that material is called a magnet, okay. And another thing you need to know about a magnet has two poles. That's the north pole and the south pole. Always two poles. And when you suspend a magnet, if a magnet is suspended, something like this, like if you tie a magnet having these poles, north and south, and you suspend it maybe with a thread, something like this, the magnet will always come to rest in its own geographical north-south direction. Okay, it has its own geographical north-south direction that the magnet will come to rest to, or that it will point to. Okay, this is very, very important. It is different from the geographical north-south pole of the Earth. So it is different from that of the Earth. So very, very important. Then another thing you want to take note of when you're talking about magnetism is that the ends of a magnet have two poles, and the power of a magnet, the strength of a magnet, is concentrated at the poles. So they might ask you, BJ, where is the strength of a magnet concentrated? It is always at the poles. That is where you have much of the magnetic field concentrating, not at the sides of the magnet, but at the ends. Okay, that's where they have the strength of the magnet concentrated in. Okay, now the force with which a magnet attracts pieces of iron or steel is what is called magnetism. Okay, it's an unknown force, it cannot be seen, but you just notice that the magnet is attracting pieces of iron, and that strength is concentrated at the poles. Like I said earlier, it's always at the poles there that you have much of those strengths. Okay, then you go to the law of magnetism. The law of magnetism states that like poles, sorry about that. Law of magnetism states that like poles, if you have like poles, they repel. Okay, that is a north to north pole or a south to south pole will repel. That means they will pull apart, they will pull away from each other. While the next one, which is unlike poles we attract. Take note of that. JAMB can ask you in exam. They can ask you, unlike poles, like a north pole of a magnet and a south pole of a magnet, they will attract. The north pole will pull towards the south pole, and both of them will gum together. You can see they will gum body, they will join together. While a north, south, what you experience is repulsion. They will repel. So that is the law of magnetism. Like poles repel, unlike poles attract. Okay, keep that in mind. Now we move to what is called magnetization. Magnetization, real quick. Let's take it real quick. Let's go. Now, magnetization, we talk about a piece of steel. How can you make a piece of steel to turn into a magnet? The process is called magnetization. That is the way you make a piece of steel, sorry about the spelling, to act like a magnet. Okay, that's the only way. So that process of doing that, of turning a non-magnetic material, a material that is not magnetic at first, or that is not a magnet, or that doesn't act like a magnet, the way of turning it to start acting like a magnet is what is called magnetization. And you can do that through some methods. You have by stroking. That's the first method, by stroking. You have to stroke the material. That's the first one, by stroking. Then you can also use what is called by method. So by electrical method, to keep that in mind. These are the two ways, by stroking and by electrical method. Now let's talk about this by stroking. You see that it's very, very simple. This question came out in the mock of last year. JAMB asked a question on the stroking method of turning a material into a magnet. Now look at how it's going to be done. It's very, very simple. The first thing to do is you have to take a piece of material like this, which was not actually magnetic before. So that material might not have north and south at first. Okay, but what you're going to take, you take a magnet like this, you put a magnet like this. That magnet will have its own north and south pole. Then you start rubbing the magnet in this direction. As in using this magnet to rub this material in this direction like this. So you'll be rubbing it. You take it up like this. You come down again. You rub it. You're using the magnet to rub the material. It can be maybe iron or steel. This could be iron. It could be steel or iron. So you're using this magnet to rub it continuously. So after a while, this material will become magnetic in nature. It will start behaving like a magnet. So they might ask you in OBJ, which side will be the pole? Will this side be north or will this side be south? Which side will be the pole? So look at how to get it. It's very easy. Once you are rubbing this magnet like this on this material, this magnet here, this north pole, will be moving all the south poles on this material to the end here, to this side. Okay, while all the other pole will remain here. So at the end of the day, this place here, this part will be south pole, while this place will be north pole. Or you can do it like this. This magnetic bar here, just bend it down. Just imagine you are bending it down like this. Just rest it on top of this material. So this place will be, this engine will be north and this place will be south. Let me draw it like this for you so you understand it better. It can also be like this. Let's assume it was like this now. So this place is south. Sorry. Let's assume it was like this. It does not have any pole. You now take a magnet and stroke it. This place was south and here is north. So if you are stroking it, they might ask you, where would this pole be and what would this pole be? So if you do that, just bring this knot here, just bring it down. Just as if you are falling it down to rest on this thing. If you fall it down like that, this place will be north and here will be south. Or use the other method. As you are rubbing this material, this magnetic material, this one here, as you are rubbing it on this one, this S that is here will be sucking or pulling all the north poles to this side. You know, unlike poles attract, right? So it will pull all the south to this, all the north to this side, while the south will remain on this side. So at the end of the day, this place will be south and here will be north. So take note of that. They can ask you in exam. Okay, so I hope you understand that part. So after a long while, this material will become magnetic. You start behaving like a magnet. So it will acquire these polarities here. Okay, let's look at the second method. The second method is the electrical method. The electrical method, that's the second method now, of turning a material into a magnet. So the second method is like this. You take what is called a coil of wire. Coil of wire that goes like this. You have a bar here. You want to turn this into a magnet, right? So you put a bar, a coil of wire like this on it. This one is passing through the back. It's passing through the back of this thing. So it will not show in this front here. So it's coming like this now. It will show in this part. It will not show. Then it will show. It will not show. Then it will show. Then this is the under part here. Then this part, connect this part to a battery like this. Connect here to a battery. So it will look like this. So when you connect here to a battery, what you now have is this particular setup here. So the current to pass through, like when the current is coming here, to pass up, pass through the back, pass up, and so on like that. So they might ask you, after a while, what will be the pole of this material? What poles will it acquire? So in the electrical method, the steel bar, this is the steel bar here, the steel bar is put into a solenoid. A solenoid is just a coil of wire. This is a solenoid here. These coils of wire that you are looking at, that's a solenoid. Okay, so you put the this steel bar into the coil of wire, then you apply direct current. Take note, they can ask you in exam which current is used. It is direct current, not AC. Not AC current, but direct current. To magnetize this bar, you use DC. So you apply DC for some minutes. So after switching off this circuit, you notice that this steel bar will have acquired some magnetism. Okay, it will start behaving like a magnet. Now, how can you know which pole will be magnetic, which pole will be north rather? Will it here be north or will it here be south? Now, look at how to know it. It's very simple. Use what is called the clock face rule. The clock face rule. The clock. It's called the clock face rule. So just look at this bar here. Let me just do for this right hand side so you get it better. You look at this bar. Let me zoom it very well. You can see this place is going up like this. This current here is going up. So if you form a circle at this point here, form a circle like this at this point here, it will look like this. This is a circle here like this. And the current is actually going up. Now this direction here is a clockwise direction. This is how the clock moves now. It's like this. This direction of the clock. So you can see that at this side here, the direction of the current in this coil is in a clockwise direction. Okay, so if it's in a clockwise direction, that will be the south pole. Okay, south pole. Then if it's anti-clockwise, that will be north pole. So you can remember it like this. For anti-clockwise direction, just use this end that is here. That will be north. Okay, and for clockwise direction, use this S here. That will be south pole. So this one was actually clockwise. You can see this is clockwise direction. So this place will be south. At the end of the day, this place is going to be the south pole. Then if you come here and do the same thing, you see this other direction here will be the north pole. So this place will be north, while this place will be south. So that's how to acquire that particular direction. If you look at this thing from inside here like this, the current is anti-clockwise. So that's how to know for that one. Okay. Then the next one you want to know is that soft iron is used for temporary magnets. Okay, if you have a temporary magnet, sorry about that. Let me just swipe this page. Temporary magnets and permanent magnets are actually different. Now, you use soft iron, what is called soft iron, for what is called temporary magnets. So you have soft iron are used for temporary magnets. Okay, like electric bell. For example, your electric bell at home it uses soft iron. Electric bell uses soft iron. That's because you don't want it to be permanent. If it's permanent, when you press the bell, the sound will not be like grrrr. You know, the reason why you can hear that grrrr is because the iron that is there, once you press the switch, the iron will become magnetic, so it will attract the striking bar, which is called the gong. The striking bar will now hit the iron, so it will make that grrrr sound. So it will now detach later. That's it, will magnetize and demagnetize, because magnetism is not that strong, so it will detach. It will not magnetize again, so it will strike as it magnetize, demagnetize. You know, it will be going like that, off and on. But if you use steel is for permanent magnets. That one is very, very, very hard to magnetize. But once it becomes magnetized, they don't lose their magnetism easily. So steel is difficult to magnetize. Steel is difficult to magnetize. But once it becomes magnetized, it will take a long time before it will lose its magnetism. While ordinary soft iron is easy to magnetize, but it loses its magnetism easily. That's why it is used for things like electric bell and relays. Okay, so steel is for permanent magnets, soft iron is for temporary magnets. Okay, now take note of that. Don't forget. JAMB can ask you in your exam. There's something called induced magnetism. That's the next part that JAMB can also ask you. So we're moving to that part now. It is called induced magnetism. Let me write the topic for you. Induced magnetism. Now, if something is induced, it means that it is not touching that particular thing. There's induced charging, there's induced magnetism. You just take a bar or a piece of material and place it near a magnet. This is a magnet here. This is just a magnetic material. Place it near it. It should not contact it, they should not touch. But after a while, this guy here will acquire his own magnetism. Okay, this side, let's assume this is the magnet like this. This is north, and this is south. And you now place it like this here. This side will acquire south, and here will be north. This guy will now become a magnet for some time. So this is induced magnetism. There was no contact between the two of them, but this one later became magnetic in nature. So that is what is called induced magnetism. So the pole induces an opposite on the ion at the end nearest to the magnet. It means that if you place the pole, if this is the original magnet here, and this is south and this is north, and you place the material like this here, at the end of the day, this place will be north and here will be south. This place here, this part will be north and here will be south. It will induce an opposite pole to the magnetic material. Okay, so take note of that. I hope you understand. Now we move to what is called demagnetization. That is the process of removing the magnetism of a magnet. Demagnetization. Okay, follow me. Let's go. So you want to remove the magnetism of a magnet. That process is called demagnetization. Now, how can you remove it? You can do it through some ways. You can do it through what is called heating. You can heat the magnet. You heat it up. Okay, you heat it to redness. The magnet will become red. They now allow it to cool in the east to west direction, not to south. If the magnet is in north to south direction, it will have strength. It can get its power back. But you place that magnet in the east to west direction to weaken it. So you hit it to redness. When the magnet is red, you now place that magnet in the east-west direction. The magnet will lose its power. Okay, it will lose its power. So that's the heating method. The second method is called hammering. You hammer the magnet. So that is hammering. So this method of hammering, you hammer the magnet until it loses its magnetism. As you're hammering it, you hammer it in the east-west direction too. A magnet will lose its power when it is placed in the east-west direction. Then the third method is the electrical method. Okay, that's the electrical method. But this time, you'll be using an AC current. Don't forget, to magnetize the material, you have to use DC. To make it to become a magnet, use DC. But to demagnetize it, you have to use AC. AC is the alternating current. So you place that material, you place the coil around it, place the coil around the material. Then you plug it to AC. To signify AC, you have to use this symbol. You draw a circle and put this sign inside it. This is AC source. Now, you place the magnet in the east-west direction too. A magnet is weak if it's in the east-west direction. So you do this experiment or this setup in the east-west direction, not north to south. So you now pass the current through the solenoid, in contact with the magnetic material. And then as you're doing that, you'll be moving this thing away slowly. You'll be pulling the magnet away. This one inside, you'll be pulling it away slowly. Okay? You will be drawing it slowly in the east-west direction. As you're doing that, the magnet will be getting weaker and weaker and weaker and weaker until the magnet is demagnetized completely. It does not have that power of magnetism again. It is now weak. Okay? Hope you understand that. Now we move to what is called magnetic fields. This part is very interesting. JAMB love this part. JAMB, they love this part. So take notes. I'll teach you how to draw magnetic fields. Magnetic field, that's the next part. Now, The first thing, what is a magnetic field? Follow me, let's go. Follow me. A magnetic field is the region or the space around a magnet where its magnetic effect can be felt. This is a magnet here. The space around that magnet where you can feel the force of this magnet is what is called a magnetic field. Okay? Just like a human being. A human being has what is called aura. That aura cannot be seen. There's some people that if you stand near them, you'll be happy. Some you'll be sad because their aura is a positive aura. So that space around that person is what is called aura. But for a magnet, the space around the magnet where the force can be experienced, what is called magnetic field. So for some magnets, for example, if you put iron here, maybe you place iron here, or nail, let me say nail. You place a piece of nail at this part. This nail might not be attracted to the magnet. The nail will still be where it is. It will stay where it is. That's because the nail has not entered the field of the magnet. By the time you move the nail closer and the nail enters the field, the nail will be attracted to the magnet. The nail will just pew, it will move and come to the magnet. That's because the nail has entered the field of the magnet. So that's the basic idea of magnetic field. The next thing you want to understand is what is called the magnetic field strength. Magnetic field strength. This one means it's a point, okay, which is a measure of the force on the north pole of a magnet. Okay, a point, okay, which shows the force on the north pole of a magnet. That's what's called magnetic field strength. It tells you how strong the magnetic field is. And a magnet, the power of a magnet is at the poles. The strength of the magnetic field is at the poles here, this ending here. That's where the power of a magnet is. Not at the sides of the magnet like this. The strength of the magnet is not at this side. It is always at the poles. That's where the strength of the magnet is. So take note of that. JAMB can ask you in OBJ. Okay? So the magnetic field strength at a point is a measure of the force on the north pole of a magnet placed at that point. The next thing you want to know is what is called the lines of force. The magnetic lines of force. This one is very important. You need to understand this one. It's very, very simple. You need to know how to draw the magnetic lines of force. I'm going to teach you how to draw. It's very simple. When you want to draw it, start from the north and end at the south. Shikina, there's no add at all. This is the magnet now. This is north pole. This is south pole. If you want to draw magnetic field for this magnet, start at the north like this and go to the south. Then put the arrow there. The field is from north to south. Not like this, oh. This one is wrong, oh. It's supposed to be north to south like this. Then go down here. We do another one like this. And don't forget, these fields cannot touch each other. They cannot cross. You cannot draw another one like this. They cannot cross each other. You understand? This one goes like this. And this one goes like this. Then you cannot put some going out like this. It always leaves the north. It leaves the north. It does not enter into the north, though. It does not enter into the north, but it enters into the south. The one for the south here, southern part now, will be entering. This one will be entering. So field strength or magnetic lines of force, they move from the north to the south. Take note of that. They can ask you in OBJ. JAMB can ask you in OBJ. How do the field strength, how can they be represented? It is from north to south. Now, another thing you need to take note of, as in the closer they are, the closer these fields are to each other, how close they are to each other, determine the strength of the field at that point. So you have something like this, for example, something like this now. You now see that the fields are much in this side. The fields are much. That means the strength of the field in this part is high. If it's the north or maybe the south, depends on whatever it is. If they are much like this, that means the strength of that part is high. And for a normal magnet, the strength of the magnet is at the poles. That's where the power of the magnet is, at the poles, not at the side here. I think I've said this before. Okay? Now, these magnetic field patterns, just to digress a little, to tell you how they got it. To get it easily, just place a magnet like this. You now place a cardboard. You place a cardboard. This is the magnet here, north south. You now place a cardboard under the magnet. Then you place iron filings. Iron, small iron like this. Small iron. Iron filings now, you understand? Place them like this. Then you now shake the cardboard a little. You notice that all the iron filings will crowd here. They will have this shape. They will form this shape around the magnet. Something like this. That is how the field is on the magnet. That is how they got the direction. So, but the iron filings, most of them will gather at this point. They will gather here. Because that is where the power of the magnet is. They will also gather at this point here. Okay, so that's how they got the direction for the for the fields of a magnet. That's how they got it. Now, you need to know how to draw the magnetic field for when you have knot and knot meeting together. This is a magnet here. So this is a magnet. You can see this is a magnet like this now. Sorry, let me just draw that. This is a magnet. This one, that magnet beside it like this. This one is knot and this one is knot. Sorry, this one is knot. So don't forget this back here will be south, Abby. This back here too will be south. You know they will repel. They're going to pull apart from each other. They will repel because like poles repel. This iron here, this magnet here, its own field will be like this. Its own will be like this. This is own field, not to south like this. Why this one here, its own field too will be like this. Its own field will be like this. So not to south, not to south. But this middle here, they cannot meet. This one will be going like this. This one will be going like this. I'm just drawing them like in a rough way, but just to understand. This place here, at this middle here, they cannot meet because they are repelling. So two of them cannot cross that point. Just as if you're standing in front of somebody. You now draw a line in between the two of you. You're saying you cannot cross this line, which I cannot cross that line. So that point in between them is called a neutral point. In most JAMB questions, you put like X here. It's not like X at this point. This point is called a neutral point. That means to this magnet and this magnet, they cannot cross that point. Two of them are saying, oh, this point, we cannot cross it. That's because they repel. They want to pull apart from each other. So if you try to force them together, both of them cannot come to this point. There's no force at this point, X. That point, S, is called the neutral point. It's called the neutral point. Okay, take note of that. Now, let's draw the one for when you have two magnets that are on like poles. So you have a magnet like this. This magnet, this one is north, this one is south. You have another magnet like this. This place is south and here is north. So because unlike poles attract, Abby, they can gum each other, they can gum body. So this one will now gum to this one. This one will gum, they will move like this. Not to south, not like this. So don't put that up like this, so you miss it. Put it like this. The north will go and meet the south. This magnet on its own, we also have its own going to the other side to meet this one. Like this. Like this. Put it north to south. North to south. This one too, we have its own. Going like this. Going like this. North to south. North to south. You can see. So this point here, there's no neutral point here. No neutral point though. Because they will gum at this point. They will meet. They will attract. There's no neutral point. The force on them is in this direction. Two of them will meet. This is it's an attractive force. So they will pull towards each other and gum body. I hope you understand. Now we move to what is called a current carrying conductor. Do you know that a wire, ordinary wire, the next topic is current carrying conductor. So we have current carrying. Do you know that a wire, ordinary wire, no magnet there, ordinary wire that is just carrying current can behave like a magnet? Yes, ordinary wire like this, just carrying current can behave as a magnet. That's why you have to be careful standing near this pole. That's why if you see where wire shock person, the person will gum there. The person is gumming to that wire because the wire has a magnetic field. Ordinary wire without any magnet near it can also gum person, can gum you, can attract you. Okay, so when you have a wire like this carrying current, maybe downward direction, this wire has a magnetic field. The field is circular in shape. They can ask you in exam. A current carrying conductor has what shape of magnetic field? The answer is circular. Okay, that's why it's circular. This conductor now can carry current in an upward direction like this. You can carry current in a downward direction. Now they might ask you, how will you get the direction of the magnetic field? So use what is called the right hand grip rule. It's very simple. This thing is very simple. Just follow me, follow me, follow me. So this is the conductor now. Let me draw it going up. This is a wire carrying current. So they might tell you to draw the direction of the magnetic field. How will you get it? Just know that you're going to use what is called the right hand grip rule. Right hand grip rule. That means you will grip this thing, hold it with your hand, and you're going to see the direction. Let me show you a picture that will give you a better idea of it. Just a minute. Just a picture that will give you a better idea of what I mean. So this is a picture here. Something like this. So this picture here will tell you the direction that the current will be. So you can see the stuff now. So if this is the wire now, this is the wire here. This is the wire carrying current up. You will now grab the wire, hold it like this. Imagine you are holding the wire with your hand like this. Grip the wire. It's carrying current up. This is your thumb here. This is your thumb. We point up because the current is going up. You can see from here, the current is going up now. Okay, the current is going up on the wire. This is I. That means yellow, so you can see it well. This is the current here on this wire going up. So you will grip the wire. Imagine you're holding it with your right hand, not left hand though. Left hand, you miss the answer. It's called the right hand grip rule. So when you grip it like this, you now point your thumb up, grip the wire like this. Your thumb is pointing up because the current is going up. That's why. If it's going down, then your thumb will point down. Okay, as if you are doing thumbs down and thumbs up. So this is thumbs up. Your remaining fingers, your 4 fingers, will now form a circular shape. You can see the way these fingers are. It's going like circular shape like this. The shape of these fingers will be circular in nature like this, around this wire, like this. And it will be pointing in this direction. See the fingers now, you can see. See the way it's pointing. See where the fingers are pointing. That is why this field is like this. That's why the field is like this. That means this, the direction of the magnetic field will have this direction. The magnetic field will have this direction. That's how to use the right hand grip rule. Okay, so you just grip the wire. This is the wire here. Grip it like this, hold it like this, and bend your remaining fingers. Bend your remaining fingers. You see that your fingers will form this shape around the wire, and your fingers will curl in this direction. Okay, that's the direction of the magnetic field. Very, very simple. Hope you understand. Then if it's carrying current downwards, if you grip it, your fingers will point in the opposite direction. Your fingers will point like this. So that's the direction of the magnetic field. I hope you understand that part. Now, something is very important. Let's move to the next one. What if what if you have 2 wires that are carrying current in the same direction like this? You can see. Just watch. They ask you in OBJ, follow up. You have 2 wires. 2 of them are carrying current in the same direction. They might ask you, what will happen to the field? Don't forget, we've already done it here that if a current is carrying wire upwards, you can see the field. The field is anti-clockwise. You can see this anti-clockwise direction. And if it's carrying current downwards, we have done it here. This is clockwise. So these 2 now, these 2 wires are carrying current upwards, Abi. So that means their field will be anti-clockwise. Draw one like this, draw one like this. Shake it now, very simple. No stress yourself, no waste your time. This one go like this, this one go like this, this one go like this, go like this. Then if you draw for this one too will go up. This one too is going anti-clockwise. So this one too is going like this. Okay. So if you notice something that at the middle point here, sorry, just a minute. Let me just confirm that the directions are correct. So this one is for, yes, carrying current up in the same direction, that's anti-clockwise. So you will notice that the 2 of them are carrying, the field is strong in this part because at this point here, you check this point, you see that they're carrying current in the same direction. The current here, they're in the same direction. Yeah. This one is going up here. This one is also going up here. They're going up in the same direction. So they will pull towards each other. They will pull towards each other. And there will be an attractive force between them. That is why two wires carrying current in the same direction, they attract. Take note of that. They can ask you in OBJ. Two wires carrying current in the same direction, they will attract. While two wires carrying current in different direction, they will repel. Okay? Two wires carrying current in different direction, they will repel. I hope you understand that part. I hope you understand. Now move to what is called the Earth's magnetic field. The Earth also has its own magnetic field. Okay, the Earth has its own magnetic field. Questions like this came out in the mock. They were asking angle of declination, angle of dip, and some other stuff like that. So it's very important that you understand this next part. So they were asking angle of declination. So the next part is Earth's magnetic field. Earth's magnetic field. So this our Earth that we are living in, it behaves like a magnet. Okay, that's your magnetic field. So the reason why is that there's something called a compass that's used for traveling. You know compass now. That has north, south, east, west. It can tell you your direction where you are going to. And the reason why it deflects most of the time is because it is being attracted by the magnetic field of the Earth. The Earth is a giant magnet. And there are regions in the Earth where the magnetic field is strong. The first thing you want to know about this is what is called the magnetic meridian. Magnetic meridian. This magnetic meridian is the vertical plane through the Earth which contains the magnetic north-south axis. A magnet has its own north-south axis. Let's assume this one for the Earth now. Let's assume this is the Earth. Let me just do the example. This is the Earth here. The Earth has its own normal north-south, right? The one that you do in geography where you have something like Greenwich meridian and stuff like that. This one is the equator, and this is the pole of the Earth, the vertical pole of the Earth, the meridian. When you hear meridian, just think of vertical line. Meridians are like longitudes. Think of vertical line. This one is latitude. That's like equator. So this one is for the Earth normally. But for the magnet itself, it has its own magnetic meridian. So when you hear meridian, it means vertical line. So the one for the Earth is like this. For the magnets rather, it's like this. It's bent somehow. It is not directly on the north pole like this. They do not meet at the point. It is bent away from it like this. It is bent away from the one of the Earth normally. This is magnetic. Let me use mm to signify it. Magnetic meridian. So it is the vertical plane through the Earth which contains the magnetic north-south axis. And the mass in OBJ, it does not coincide with the north south of the Earth. It does not coincide with the Earth's geographical meridian. You can see they are not meeting at the point. There's a gap. There's an angle in between them. The angle can be theta. There's an angle in between the two of them. They do not coincide. They don't meet at a point. Now, that angle is what is called the angle of declination. Let me draw it here. You have the Earth. You have the north, south, Abi. Draw that one down. Draw that one down. This is not the magnetic meridian. Bending away from the real north-south of the Earth. This is the magnetic meridian. That angle that is in between them like this is what is called the angle. They call it the angle of declination. JAMB asked this question in 2024 mock. They asked this question in 2024 mock. So the angle of declination is the angle between the magnet, okay, the magnetic meridian and geographical meridian. The angle between the magnetic meridian, you can see magnetic meridian here, and the Earth's meridian. The angle that's between them is called the angle of declination. Move to the next one. A freely suspended magnet, a free magnet that you just suspend, you tie it to a ceiling. That magnet will always come to rest in the north-south direction. It will point to as in, it will come to rest horizontally in the north-south direction. But there's a funny thing. It will not come to rest exactly on the equator like this. It will not be flat. It will be a bit bent. It will be something like this. It will be slanting somewhere like this, north-south. It will not be exactly horizontal like this with that of the equator. No, the equator is a horizontal line, Abi. It will not be exactly horizontal. So there will be a small angle. This is the horizontal line of the Earth now. This is something like this, the angle that the magnet will bend to. It will not be exactly horizontal when you tie it to a ceiling like this. So that angle that is in between the magnet itself and the horizontal line, that angle between them is what is called the angle of dip. You call it angle of dip. This one can be theta here. Okay, so angle of dip can be defined as the angle which the axis of the magnet makes with the horizontal. You can see horizontal line. For angle of declination, it is the angle which the axis of the earth, which the axis of the magnet makes with the vertical plane of the earth. Angle between the magnetic meridian and the earth's geographical meridian. The angle is called angle of declination. Angle between the axis of the magnet. Angle between the axis of the magnet and the horizontal line. That is what is called angle of dip. Okay, so this brings us to the end of the basic things that they can ask you under magnetism. But now, we'll move to what is called the force on a current carrying conductor. Now, this is what is called Fleming's left-hand rule. So before I show you that, let me just show you the picture so you have an idea of what it looks like. So Fleming's left-hand rule can be used to find the force that is acting on a current that is carrying, a coil that is carrying a current. So it's something like this. So I'm going to use this diagram to explain this part now. So just stay with me, okay? Stay with me. Let's go. We're going to cross this jump. Stay with me. Now, let me just keep this part a bit. So the topic now is force. The topic we're doing now is force on a the current carrying conductor. This part is very important. Follow up. Let's go. Now, a current carrying conductor placed in the magnetic field will experience a force. Take note of that. This is what you have in rotor. So you have a magnet like this. This is not. Place on that magnet here. Another magnet here. This is south. You now place a wire in between them. A wire. This is the normal feed for this stuff. The normal feed is like this. North to south. It will be like this. You now place a wire in between this feed, carrying current maybe up or down. This wire will experience a force. It will shake. Now, depending on the way this wire is in this field, maybe it is slanting like this or bending like this. Depending on the angle, it will determine the force that this wire will experience. If the wire is entering this field vertically like this, you have the field vertical, as you can see here. This is the field horizontal, but the wire enters vertically like this. This wire will rotate. You can ask you, Joe, follow up with me. If you have a field like this, a field going like this, and a wire is placed vertically like this, or even a charge enters the field vertically like this, this wire will experience a force that will cause it to move in a circular fashion. This is what you have in rotor. That rotor that you have in your fan, generator, and all those things, this is what is causing it. It is the force on a current carrying coil that is causing it to turn. Now, that force can be obtained using what is called Fleming's left-hand rule to know the direction. So you place your left hand like in this shape. Your thumb, your index finger, this finger here, will point in the direction of the magnetic field. This one will point in the direction of the current, while this other one will now give you the direction of motion. So to simplify it here, to know where this wire will move to, I'm going to give you an example now. So this is north, this is south of a battery of a magnet. So this is the field normally. It's like this. So the field will point in this direction. So your index finger will point like this. This is your index finger like this. Now the current now. This is the wire carrying the current. Let me say it's going down. So this is your middle finger. That's the tallest finger. You point it down. Okay, you point it down like this. This is your your middle finger, the tallest finger in your hand. This is it here. This is your index finger, the one that is next to your thumb. This is it here. Then if you do that, your thumb will point in this direction. If I haven't tried it, that means this wire will move in this way. This is what is called the Fleming's left hand rule. The wire will experience a force which will cause it to move like this. Or it can move towards the observer as it moves towards you, as it moves towards your screen, rather. Let me just put it like that. So Fleming's left hand rule, the force that the wire is experiencing can be changed depending on some values. It depends on some values. The force on Fleming's left hand rule or the force on a current carrying conductor can be influenced, or it depends on some factors. The first one is magnetic strength. That means if you're using a bigger magnet, this magnet is very big, or a stronger magnet, then this wire will move to move very fast. It will experience a greater force. That's the first thing that will affect that the force will depend on. Another thing is the length of the wire. Length of the wire. If this wire is long, this wire in the field, if it's very long, then the force will also be greater. And the third one is the current in the conductor. If you use a high current, then you experience a high force. Small current, you experience a small force. So the force on the current carrying conductor is given by BIL sin theta. This is it here. Very important. I'm going to ask you, take note of, follow up. The force is given by F is equals to BIL sin theta. Now, what is B? B is called the magnetic flux density. Don't let it confuse you. Don't let the name. It's just a fancy name. It just means that if something is dense, it means it's heavy, Abby. How concentrated are the magnetic field? If magnetic field are much at a particular part, the magnetic field here, they are much at a particular part. That means the density of the field at that point is high. I know in a normal bar magnet, the fields are higher at the poles like this. If it's not on south, the fields are higher here. That means the density of the magnetic flux at this point is higher. This part is also higher. So magnetic flux density just means that how concentrated are the magnetic field? Is it much? Is it few? That's the meaning of B. And this B, the unit is Tesla. That's T. I is the current that is flowing through the conductor. That I is measured in amperes. While L is measured in meters. L is the length of the conductor. How long is the wire? Y sin theta or theta is the angle with which the wire is in the field. So just bear with me. I'm going to explain it with this diagram now so you understand it better. So if this is the field here, like this, and this is the wire here, the length of this wire, how long it is, that's the length. Okay? If it's very long, the force will be greater. This is the field here. How strong is the field? This is the field here. How strong are they? Is it a permanent magnet? Is it a strong magnet? Then the force or this wire we experience will also be greater. Then the next one is the current flowing through this wire. Is it a high current? This small current. If it's a high current, then the force will be greater. It will turn faster. You have a rotor. You plug a rotor to a small battery. It will turn very small. Plug it to a bigger battery. It will turn very fast because the force is higher, because the current flowing through the conductor is now high. That's why the formula is F is equals to BIL sin theta. Then for this theta, which I have not explained, this theta is the angle with which this conductor is placed in the field. It can be like this in the field. It can be vertical. It can be horizontal. Depending on the orientation of the wire in the field. Now the mask in OBJ. At what point does the wire experience the greatest force? Just look at sin theta. Sin theta is always maximum when theta is 90, Abi. Because sin 90 is 1. That's the highest value you can have for theta. You can never have anything greater than 1. Sin 90 is 1. That's the highest value of sin theta. So the highest value that this thing can be is when everything here like this is equals to 1. If everything here is equals to 1, then this formula will change. It will be BIL times 1. And what will you get? You will still get that BIL. So that means F is equals to BIL. This will only happen when the conductor is at 90 degrees in the field. The conductor is vertical, like this is the field here. The conductor is vertical. The angle between them is 90. This is the wire here. It is vertical. It will experience the greatest force when it enters the field in a vertical direction. And when the conductor enters in a vertical direction, the wire will rotate. Take note of that. The wire will experience the greatest force when it is perpendicular to the field or at 90 degrees to the field. And the wire will also rotate to turn in maybe clockwise or anti-clockwise direction. Okay? So take note of that. At any other angle, maybe 30, 60, the force will not be great. It will be minimum. And the force will be 0 when the conductor is parallel, because sin 0 is 0. This is the conductor here. You place it like this. It will not experience any force. It will just be there. The force will be 0 because it is parallel. Look at the formula now. See. F equals to BIL sin theta B. This one is now 0. That means sin 0. 0 times all this one, you also give it 0. That means F is equal to 0 newtons. It will not experience any force. It will just be the way it is. So you understand that part. So this is a very important thing. So use Fleming's left-hand rule to get the force that is acting on a current carrying conductor. So that's the next. That is very, very straightforward. Okay. Now, that formula can also be used for a charge. If it's a charge, instead of a wire, you have a charge. The formula will be the same thing. If you look at this, F equals to QVB sin theta. So this Q is the charge. V is the speed of that charge, velocity of that charge. This one is the value of the charge. This charge is measured in coulombs. Abi? Velocity is measured in meter per second now. You know what is B already now? B is the flux density. Y theta is the angle with which the charge enters the field. So if this is the field here, like this, and the charge enters it in a vertical direction like this, that charge will rotate. It will move in a circular direction. They can ask you in OBJ, take note. If a charge enters a field at right angle like this, it will turn. It will turn. That's what is in rotor. It will turn. So the direction of that force can also be obtained using what is called a Fleming's left-hand rule. So the force causes a charged particle initially moving in a perpendicular direction in the magnetic field to go round. It will go round. Now, if you want that force, this wire to move in a horizontal direction, you place an electric field E, which has the same strength as the magnetic field M. You place them, so you have something like magnetic force and magnetic electric field. So once two of them meet, they are equal in number. It will cause the charge to move in a straight line. That's if you want the charge to move in a straight line, you place a magnetic field and electric field. Both of them will have the same value. So it will cause the charge to move in a straight line, maybe horizontally, maybe like this or like this. But if you want it to move circularly, like you want it to rotate, just let the charge enter the field at 90 degrees like this. Then it will rotate by itself. It will turn in a spiral direction. Okay, I hope you understand that. So move to what is called electromagnets now. Now, for electromagnets is very, very important. Follow me. Let's go. Electromagnets is electromagnet. Let me just write the topic. Electromagnets. Electro. So electromagnet is made up of winding wire coils in opposite directions around the arms of a U-shaped soft iron bar. Very simple. The electromagnet is not hard, not stress yourself. Just have a bar like this. You now wrap wires around it. That's the electromagnet now. You wrap wires around it like this. You wrap wires around the magnet or around the bar like this. This is electromagnet. You can now plug here to a battery, something like that. You can plug it to a battery. So this is electromagnet. Don't forget, electromagnet, you cannot use steel for electromagnet. Steel is not used because steel is permanent. Once steel becomes magnetic, it does not magnetize easily. So you cannot use steel for electromagnet. You can use what is called soft iron bar or core. So take note of that. You only use soft iron for electromagnets because they can magnetize easily. They can easily become magnets, but they lose it easily. You understand? But steel, this is why I cannot use steel, because steel is very hard to magnetize. So you don't need that. This is very, very hard. But it will lose magnetism. It will take time before it loses magnetism. So the trick here is this is a solenoid. You tie a wire around the iron bar like this. Then you plug it, you turn it on, to a current source like a battery. Now this guy here will become magnetic for the time when the current is flowing. If the current is flowing, it's not magnetic again. No. So when current is flowing, that will be magnetic. But once you remove the current, it will no longer be magnetic. The magnetism lasts as long as the current flows. So without current, it will just be ordinary iron. But once there's current, it will be magnetic in nature. So the strength of that magnet, okay, we increase the strength of the magnetism, the strength of this guy. Okay, how strong you want it to be a magnet? That strength will increase based on some factors. Number one is the number of turns of coil. The number of turns of coil that you have. That means the number of these red wires that you tie around it like this. If that number is much, then it will be the strength of this magnet will be strong. But if the wire is few, then it will not be that strong. So that's the first thing that affects it, the number of turns of the coil. The next one is the current induced. Okay, the current that is used. If you increase the current, that is high. The current that is flowing here. If the current is high, then the strength of the magnet will also be high. Then the next one is if the poles are made closer. The poles are made closer. If you're using like something like a U-shaped iron bar, instead of it something like this now. You now use something like a U-shaped iron bar, something that looks like this. This is something like what's in transformer. So when you wrap the coil around it like this, you wrap the coil around it like this. You wrap the coil. You just wrap that around like this. The strength of this magnet will be higher if these poles are near each other. As in, this is what I mean. Like this. Look at this one. Okay, and look at this one. In this one, the poles are far apart. See, look at this distance now. They are far apart. The strength of the magnetic field will not be that high. But this one, they are near each other. This distance is very small compared to this distance. This one has there's something called induction. The fields can enter into each other. Okay, so there's induction there, which will strengthen the magnetic field. So this one have greater magnetic field, while this one will have a smaller magnetic field. So these are the three factors that can increase the magnetic field of an electromagnet. So I hope you understand that and you are moving on. So this is just some basic things that you just need to know about electromagnetism. So let's take the last part, which is galvanometer and ammeter and so on. So I'm going to start with the galvanometer. So a galvanometer is a current detector. Don't forget, they don't need to measure current. The function of galvanometer is current detector. This is to detect current. If you want to know if current is in a place, if current is somewhere, so this have current, then use what is called a current detector. This is a galvanometer. So this is the symbol here, G like this. That's the symbol of galvanometer. But at times they used to measure small current, not high current, small current, like current that are like milliamperes, like 2 milliamperes, not like 50 amperes. It's going to blow. Like small currents, like 0.5 milliamperes, small current like that. So you can use to measure small current. Okay, it consists of just a normal coil, just like a coil too. Okay, a rectangular coil. You have something like a bar like this. That's inside it. Then you have coils around it like this. So it has a pointer too. That pointer will be pointing on a scale, like a scale. So you can tell you this is 2 ampere. You have maybe like 0, 1, 2, 3, 4 ampere. It will be like a speedometer of a car now. You understand? It will be moving, it will be deflecting. So once it's deflecting, it will be telling you the current that is flowing at a particular point. So it's electromagnetic in nature. It works on the motor effect. So it has there's something called air spring inside it. Air spring. The function of that air spring. JAMB asked this question, I think last year. So what's the function of the air spring? The air spring is connected to each end of this thing. It is to pull this thing back when it is deflecting, so it does not deflect too much. It's like a spring. You know what the function of a spring now? To bring you back to the initial position. Okay, so it produces like something what is called a torque. A torque is just a rotating force. This one is going like this. This one is coming down like this. So it causes rotation, right? So that torque, it will pull the pointer back to where it was before. Okay, so once you detach this one, it will go back to maybe 0 mark. When you connect it again, it will move to maybe like 3 milliamperes. If you're not using it, it will go back to how it was before. So you can be on 0 in its resting position. So the coil comes to rest at a position in which by the current exactly balances the resisting torque of the air spring. So you have the current that you have measured like this. You have a current. Once you measure the current, that spring will deflect. Once it deflects, it will stop at a particular point. The point where the current balances that moving force, the point where they are equal. If it has 4 milliampere, just stop there. Then that air spring will now pull this thing back to 0 to stay how it was before you measure the current. So that's galvanometer. Then ammeter is used to measure current, and it must be placed in series. The symbol for ammeter is like this. And if you want to measure current, you place this ammeter in series. This is what you want to measure. This is a radio now. Radio. You want to measure the current in the radio. You place the ammeter like this, in series with it. Not like this. Not like this. This one is for voltmeter. You place the ammeter on the same straight line with the radio. Then you can measure the current. So the current that's entering the radio will also pass through the ammeter, and you will just see the value there. So an ammeter is an instrument used to measure large electric currents. Galvanometer is to measure small electric currents. So ammeter is for large currents. Ammeter will measure large currents. Okay, of the order of like several hundred amperes, like maybe 50 amperes, 70 amperes. Use what is called an ammeter. But for small currents, use what is called galvanometer. So it's always connected in series. Don't forget it's in series. And an ammeter must have some factors. An ammeter number 1 must have what is called low resistance. An ammeter must have low resistance because it is always connected in series so that enough current will pass through it. So you're able to measure what you want to measure. So place it in series. Okay, so you place it in series so that it does not affect the magnitude of the current that is flowing. Enough current to flow through what you want to measure, then you get the value. No, low resistance will allow much current to flow. I equals to V over R. You can see it from here now. That means current and resistance are inversely proportional. The higher the current, the smaller the resistance. And since you want much current to pass through, then you must make this one to be small. So small resistance, high current. Once the high current passes through the material, you can now measure it with the ammeter. So it's easy like that. So resistance and current are inversely proportional. Don't forget that. Now, they might ask you, how do you convert a galvanometer to an ammeter? Galvanometer. Want to convert galvanometer to ammeter. It's very simple. Use the galvanometer here. You connect what is called a shunt. A shunt is just a resistance. A shunt. You connect it in parallel, like this, to the galvanometer. This galvanometer will now turn to an ammeter. You can see I'm using low resistance shunt to return to an ammeter. To convert galvanometer to ammeter, a low resistance conductor known as a shunt is connected in parallel to the galvanometer. So take note. Let me take it again. To convert galvanometer to ammeter, convert or use a low resistance shunt in parallel with the galvanometer. Okay, so that is how to convert galvanometer to ammeter. Why? So hope you understand that part. So enough current will pass through this part because this one has a small resistance. Don't forget, galvanometer cannot take too much current though. It will blow. That's why you have to allow plenty current to pass through this shunt. This shunt has low resistance. So enough current will pass through it. Then this one will now measure the small current that is passing through. Okay. Then the last one is voltmeter. This is the last part. Thank you for watching. I really appreciate you guys. You guys are wonderful. I really appreciate. So the next one is voltmeter. A voltmeter measures potential difference, PD. That's what it measures, PD. It measures PD. And you place voltmeter in parallel. This is what you want to measure the volt. This is a radio now. You place voltmeter like this. This is a symbol of voltmeter. Place it in parallel. Not like this, so. Don't place it like this, so you miss it, oh. Not like this. Don't place voltmeter like this. This one is for ammeter. This is how you place ammeter. In series with what you want to measure. But for voltmeter, you place it under it in parallel like this. In parallel. So voltmeter can be used to, it is used to measure the PD. Several, like 50 volts, 70 volts. And a voltmeter must have something, high resistance. It must have a high resistance. And it's always connected in parallel. So voltmeter must have high resistance. Okay, high resistance so that little current can flow through it. Don't forget that current and resistance are inversely proportional. So you must connect a high resistance so that small current will flow through it. Then the next thing, to convert galvanometer to voltmeter, this one is very simple now. To voltmeter, you have to connect a high resistance multiplier. So this is a galvanometer here. You want to turn it to a voltmeter, is the galvanometer. This is how you connect it. You connect a multiplier. Multiplier just means resistance that has a very high value. So ROM is a multiplier. That's why I call it ROM. So the value is very high. People like 900 ohms. It's very, very high. So you connect it in series with the galvanometer like this. Okay, so that small current will pass through it. Then from there, it becomes a voltmeter. So only a small fraction of the PD to be measured is applied across the galvanometer. Only a small fraction is applied, while a large proportion is applied across the resistor. So you can see that we have different PD. Because this one have V1, this one can be V2. When materials are placed in series, they have different PD, but they have the same current passing through them. The same current will pass through them because they are in a straight line now. They are in a straight line, so the same current will pass through. Okay, then take note of the fact that to convert galvanometer to voltmeter, you place a high resistance multiplier in series with it. Okay, I hope you guys enjoyed this short introduction, this short quick revision for magnetism and electromagnetism. I hope you enjoyed this video. Thank you for subscribing to Endu Maths. I really appreciate you guys. You guys are wonderful. Thank you. Remain blessed. Thank you for watching this live. Okay, I really appreciate you. I'm going to do another one very soon. Okay, thank you for watching. Remain blessed. Peace.